Barbara Wagner from the Institute of Mathematics of the Tech University in Berlin, and also at the Weierstrass Institute in Berlin. And Barbara will talk about apparent slip for an under-convected Maxwell fluid.
Upper convected.
Upper. How do I read under if it's upper? Okay. Should we probably tell us the difference?
No, actually not. Well, first of all, let me thank the organizers for inviting me here, and which is a wonderful place to do work and meet new colleagues and start new collaboration, which we already try to do. So what I would like to tell you about here is, first of all, I will spend a little while before I come actually to the apparent, the upper convected Maxwell fluid. I will tell you a little bit about, well, quite a bit about our motivation and what we want to do with considering such a model. And let me, how is this done? I think like this. Our work on this part of research started with some experiments several years ago by the group of Karin Jacobs at the University of Saarland. And what they do, they take a silicon wafer, which is coated by silicon oxide, very typical, and then they coat it with 3 different materials. These are polymer, grafted polymer chains. So you have a monolayer of, which I will call DTS. Another monolayer is here OTS. These are different lengths of the same type of polymer, and also a nanometer layer of Teflon. And on top of it, they put like about 100 nanometer thick layer of polystyrene. They have spin coated before, and then some procedure on how to put this onto the substrate. And then they heat it above the glass transition temperature. And what they see, this is all of them are hydrophobic coatings, hydrophobic to polystyrene. And what they then see is that polystyrene will rupture at some places and de-wet. This is a complex de-wetting process going on. Here are some pictures of what they see. Oops. For example, here's one hole that has formed after rupture. Then what happens is that at the border here, the liquid from the outside will be collected, and while this rim grows, it forms instability, forms this nice pattern of these protrusions, and these form these droplets. They eventually pinch off, and you get a nice pattern. And this is a pattern you get when you have OTS or also a DTS coating. Interestingly is this one, some more recent experiments where you coat with, for example, DTS, and also coat the substrate with Teflon layer, and change nothing else. Everything else remains the same, and you see completely, dramatically different patterns. This is an overlay of the rims. They follow in time, but this here is an overlay when the film or the de-wetting film or the rim has traveled 10, 20, up to 60 microns. And so we follow the form or the shape of the rim if we look from the top onto the film. And you see when you coat it with Teflon that even after 60 minutes you see still rather shallow, sort of symmetric blobs. While when you coat it with DTS, and similarly this happens with OTS, you see rather much earlier, you see a very asymmetric formation of shapes. You have these finger-like protrusions coming out on the duetted side. And these protrusions then form these droplets and eventually pinch off. So it's dramatic, this, just a different coating. And this was the motivation. This is what we want to understand. So I tell you a little bit about it, how we went about to model this. Well, these are some later pictures of DTS, OTS coating and a Teflon coating. So they also look later on also much different what you see in the remaining part. So the driving force in all of these are the intermolecular potential or intermolecular forces. They are a combination of van der Waals forces, contributions coming from the different layers, from silicon oxide and the top layer. It turns out that when you measure or determine the Hamaker constants, that only the top layer has a dominant contribution to the van der Waals forces, and this is balanced by the Born repulsion forces, and the combination of this gives a potential that has a minimal height that is remaining after the film has duetted. So this was one of the first observations they made in the experiments. This is a cross section of a rim where you coat it with OTS and with DTS. And again, change nothing else. And what you see if you look at the back side of this rim and look at it with a logarithmic scale, you'll see that the back side decays in an oscillatory manner for the OTS coating, while the duetting rim, the backside of a duetting rim, has a monotone decay for the DTS layer. This is what we could explain first. For one thing, what they told us, since nothing else changed, only the layer, is that it can only be friction at the solid-liquid interface that will effect this transition from oscillatory to monotonic decay. So this is when we started looking at a model. Of course, we have a polymer, but we thought, since this polymer, what they used for polystyrene are polymers with a molecular weight that is below the length of the entanglement. And so for the slow duetting, we said, okay, we can assume it behaves almost like a Newtonian liquid. And so we go just about the usual modeling. This is the conservation of momentum, conservation of mass. Then we have boundary condition at the capillary interface, which are the tangential balance and the normal contribution added here with the disjoining pressure coming from the interfacial potential, coupled with the kinematic condition. This is the stress tensor, just the usual thing. Then we have the conditions at the interface. Of course, it's impermeable, but what we change here is we assume a Navier slip condition that is associated with that friction. And what we did is, because we want to model and capture all the dynamics, doing this in an efficient way, we want to derive somehow some simplified models like lubrication models for this situation. So we asked ourselves, if you go through orders of magnitude of the slip coefficient, just changing in this whole system only that one parameter, going from, say, 0, no slip, to infinity. Of course, your flow field will change from parabolic to a plug flow situation. So we asked ourselves, what is doing a systematic asymptotic treatment of this, what's possible? And this is what we found. We found basically two distinguished limits. One we call the weak slip limit, which is actually was something that was well known before these types of lubrication equation. In the limit when B goes to 0, the slip length, we obtain the classical no slip model. And we found a new distinguished limit that we call the strong slip limit. That's the limit when the slip length is of order 1 over epsilon squared, epsilon being the small number for the that accounts for the scale separation of the horizontal to the vertical scale. And so this is not anymore a scalar equation, but a system that couples the horizontal velocity u with the profile h of the film. Actually, if beta here goes to infinity, you do recover another classical equation, namely the equation for a free film separating or extending. What is important for us is both of these weak slip and strong slip limits have a limit in between. We call it the intermediate slip limit. So if beta here goes to 0 and B here goes to infinity, you end up with the same model, which is very similar to the no slip model, but it has an h squared mobility instead of h cubed. And that makes all the difference, we'll find out in a moment, and that explains a lot about the instabilities we see. Here's one first observation we saw is, and this is now not the experiment, these are numerical simulations of the strong slip model for the cross section of a duetting rim. Because in the models you see here, showed you before, at that time at least we knew how the structure of for the cross section, how they looked like. They all had this one, they all had the property that the backside of this rim has an oscillatory decay. We all know this from lubrication theory. The only one we didn't know was the strong slip model. So, of course, we looked what happens here. And indeed, we saw there's a critical slip length where you do have a transition from oscillatory to monotone decay. And you wrote a couple of papers on this comparison, and first qualitative and later on also a quantitative comparison compares quite well. So that was our first success in our models. In the meantime, we also checked with other colleagues if it possibly could be a viscoelastic effect. So we put in Jeffreys types models into our models, and we saw that only if you have large slip you can see this transition. So this is really a problem that, or the phenomena that comes from the friction, from the slip part. It's not viscoelastic. That was actually suggested at that time, that is the cause. And also a PhD student of mine and colleagues in the meantime also proved rigorously existence of solutions for these models. So we worked quite a bit on this. The other thing, now coming to the intermediate slip model and to the instability I've showed you at the beginning, is that if you look at the strong slip model and you start the wetting process, these are just numerical simulations. So you start the duetting process and you look at the duetting rates, or look at the profile of the duetting rim. And what you see is this here is the exponent over time. As the rim grows and the film duets, you see all of them, no matter how large the slip is, all of them eventually, after a long, long time, as you see here, will approach the t to the 2/3 law. Now, what does it tell us? It tells us if you look at some matched asymptotics calculations for the no-slip model, then the development of the contact line is about linear with some logarithmic corrections. So the de-wetting rate here is almost constant. The same thing is true for the strong slip model, even though here, in the meantime, John King and Andreas have produced a number of papers where they analyze this case. This has a number of regimes, but for this, one can say it's almost constant, the de-wetting rate here. Very different for the intermediate slip model, because here we find out that the evolution of the rim goes with the law of t to the 2/3, and that means the de-wetting rate is t to the minus 1/3. What does that mean? What this means, I'll tell you in a minute. Before, I wanted to tell you this other comparison with experiments. Here you see experiments of a de-wetting rim, the cross section again, and as it grows, you see a transition of, well, these data are not that good, but you do see it here, a stronger and stronger oscillation coming about. And this is something we see also in our numerical simulation for the data of this experiment. So this is something that signifies that we have a transition to a model that has this oscillatory behavior. And if you look at the evolving rim and at the shape of this rim, you also see, when you normalize this, that it has a particular shape. Namely, if you take a line here in the middle, that this distance from here to here is about 3/2 the distance from here to here. There's a particular shape, namely the shape the rim has for the intermediate slip model. And you see that for starting with a very strong slip, eventually as the rim grows, it will attain this shape. These are the experiments. And that has, we will see, something to do with the instability. So a little bit earlier on, we looked at the stability problem for the intermediate slip model, where the mobility is is 2, and also the no-slip model, just for comparison, where the mobility is 3. So the problem here, though, was that de-wetting, if you do the linear stability analysis, it's not completely straightforward because the de-wetting rim grows. So we have a situation here where the base state is not constant. And so you cannot just go to Fourier modes and so on. So early on, what we did is to do this numerically. We take a range of wave numbers and at the same time couple this with the numerical simulation of the growing base state. And then monitor the shape of the perturbation and the amplification factor. And you can see already one interesting thing. Namely, here are some, as an example, wavelengths where you look at it at different times. And for ease of comparison, we scale everything to 1, here 2. This is the intermediate slip case, here's the no-slip case. In the intermediate slip case, you see that the front is perturbed, but the back is hardly perturbed. While for the no-slip case, the situation becomes much more symmetrical. And so you see already in the linear stability analysis some asymmetric behavior here. Remind you of the asymmetric shape at the beginning of this of my talk, at the pictures you saw, and a more symmetric situation here. These are a numerical simulation of the full model, showing the asymmetric shape of a perturbed de-wetting rim, and the symmetric shape of this rim. And here are some experiments. This is not a quantitative but a qualitative comparison. And a bunch of papers we wrote about this instability as well. I should say, I told you a little bit about the wetting rate a minute ago, and told you also that it has something to do with the instability. And that's some heuristic going back to Prof in a very early paper where they did a scaling analysis and had already an idea about this instability. And the basic is it goes to this de-wetting law, which is t to the minus 1/3 and not constant. T to the minus 1/3 says that as the rim grows, the de-wetting rate slows down. Now you imagine you have a rim that grows and you perturb it. So you have bigger places and thinner places. So the bigger places will be enhanced and will grow slowly, stay behind basically. And the thinner parts, they will de-wet faster. And so this explains the asymmetry in a heuristic way. Now we've done this also using equations and numerical simulation. But this is something, a mechanism that was interesting to understand. So it's not the typical mechanism of instability you see from thin film that flows down a plane or something. It's a completely different mechanism. And also a completely different driving force. So far, this story, this has been taken us quite far and for some years. The only thing, or not the only thing, but one thing that bothered us is that ad hoc assumption that there is this large slip. Where does it come from? This is something that has a signature coming from what's going on at the interface between polystyrene and the substrate. So we looked a bit around what has been there. There's been quite a lot of work being done on shearing polymers, and depending on the type of polymer, on the length of the chains, you can have, and on the grafted chains on the substrate, you can have various different explanations for this. There's one big group around Prof and Dejean talking about long chains that disentangle. So the bulk chains will disentangle from, say, grafted chains on the substrate. Our chains in the experiments are possibly not long enough for that. There are also theories going back to actually Armstrong, Brown, and Bave very early on the alignment of the chains near the substrate. And due to the alignment, the flow practically doesn't see the chains, and so they do not contribute enough to the viscosity. So all of these theories have in effect that you have a boundary layer of lower viscosity near the substrate as compared to the bulk. And that serves as the interface appears to have a finite slip. So there's a thin layer near the boundary where you have a different conformation of the chains. So this is a typical polymer quality. You won't have this with a simple fluid. And the other thing is that the response of such a polymer to structure or to introduce this spatial inhomogeneity is that you can, and as I mentioned, there have been quite some works actually going back to El Carré and Lille to introduce, or not to introduce, but we can derive actually terms that model this as a stress or migration diffusion term. So you include in your typical stress equation, you have an additional term that is representing the spatial diffusion. And in our case, for melt, and we look at the most simple case, we will include just this one diffusion term in our model. Of course, we need to introduce boundary conditions then for the stress equation. They can be model the alignment and the net flux of conformation, which is typically 0. So let me show you what this is. Just the beginning, in a way, that we want to capture this simple effect of slip with a possibly what's the minimum model to capture this. It was our question, instead of using this ad hoc Navier slip condition. And can we recover our models that have done so well from such a description? So here we are. We have the momentum equation, mass equation. We have a stress tensor that has, in addition to the Newtonian constant stress, a contribution coming from the polymers, or the polymer stress, that is governed by, and here we take just the upper convected Maxwell model, plus some diffusion of the stress. That's the addition we allow for the stress. This is the upper derivative here, and the polymer stress, or has here G naught, which is the for monodispersed polymer. This is the plateau modulus that typically has a plateau, and this together coupled with the relaxation rate of the polymer, or relaxation time of the polymer, you get the contribution for the polymer viscosity. And then for the capillary interface, you have your typical normal and tangential conditions, and kinematic conditions, plus, as I said, here we took, that's up for discussion, but here we took the boundary condition of no net flux of conformation, either through the capillary interface nor through the liquid-solid interface, and no slip condition at the substrate. So, in order to derive lubrication equation, we again scale, use the separation of scales of horizontal to vertical scales, and here we scale, in addition, we scale the hydrodynamic pressure larger than the polymer stress, and I won't write down the whole scalings here, just that what is different, and pressure and balance the pressure in the boundary condition for the free interface for the surface. We balance pressure and the surface tension to get that number, set this to order 1, and then we get the small parameter epsilon to be of this this type. So we get this momentum equation, the deviatoric stress equations, and what I wanted to say with this slide, without you looking at all of the terms, keeping in mind that epsilon here is small, we have parameters which are the Reynolds number, the de Borah number, and 2 additional numbers, beta and delta. Beta here, and these will be the controlling parameters that control the basically the shape or the signature of the flow profiles. Beta is a ratio of the Newtonian viscosity over, if this becomes large, over the polymer viscosity, and delta is in a sense an inverse diffusivity. And before, since we have now, if we don't think about the de Borah number and the Reynolds number, we have now basically 3 beta, delta, and epsilon parameters that could possibly be small. And if you want to do asymptotic theory, you are in a big mess. You have to decide which one is the smallest and which limit you need to take. To get some insight into this, we looked at a very, here the boundary conditions I forgot to mention, but so you have your boundary conditions at the capillary interface, which have additional terms, of course, coming from the stress. And you have boundary conditions of no net flux and the kinematic condition, and no net flux here, and no slip and impermeability. Now, we looked at, to educate us a bit what's happening with our model, at the channel flow. Because using channel flow, you can write down the solution explicitly and see what happens. So what happens? Basically, the solution has 2 parts, one coming from the parabolic flow field, and the other one from the boundary, from the diffusion part. Now, if you look at these 3 different pictures here, and you see when you decrease beta by orders of magnitude, and look at all of these 3 cases, you see the appearance of boundary layers as beta decreases. See it in particular, let's look at this black curve here. If you decrease beta, you have a boundary layer when here, and you still have, though, a parabolic flow profile. If you then, and this delta was 10, so we think of it as large. If you decrease delta, if you take a delta, that's the inverse diffusivity. If you take delta 10 to the minus 2, you think of that as small. You look at the blue line, you see that also, in addition, you have a transition to a plug flow type regime. So these 2 parameters control the flow field, and beta being small leads to boundary layers, and on top of it, delta being small leads to a plug flow transition. And the combination, the square root of these, gives you actually the boundary layer thickness. So this is for us, yes?
Also, did you ever think of it that way?
No.
Okay, yeah, what happens is that as you increase the Reynolds number, the boundary layer gets thinner, and the nose of the profile becomes flatter and flatter.
I see.
Yeah, you can just take a look at some elementary book on turbulence, and you'll say, why is that so similar?
Well, let's look at the equations. Maybe there's some similarity in
People talk about that.
yeah. But here it's about explaining complex liquids, the behavior of the polymer, what happens at the boundary, what does the polymer do at the boundary, how does it respond to the shearing stress. And so quantified in these numbers, this is what it controls. Controls the different form, and this is what controls the boundary layer thickness. So if you want to do asymptotics and deriving thin film models, this is your small number, which we use now to take from our model, to start from our model and derive a sharp interface model. Sharp interface, and that's the basic idea to get eventually to the lubrication model. We want to get a model that is models the bulk flow and has at the it has a sharp interface at the boundary, and we want to derive the right conditions at this boundary, thinking of slip conditions. So now let's look still at the channel flow, because now we know the solution. Take here the alpha going to 0, having delta first of all, order 1. This is what you get. It's a very simple calculation. And since there's a boundary layer, we introduce a boundary layer coordinate. Take the limit alpha goes to 0, you get this one. Of course, when zeta, the new boundary layer, goes to infinity and z goes to 0, they of course match. And you get a new condition here. That's the condition at the new interface of the outer flow. So that's an approximation of the channel flow, if you like. And the other interesting thing is if you look at the flow field U, take the absolute value over the shear rate, basically at the at plus or minus at the upper and lower plate, and then you see you get a number 2 over delta, and that is what we interpret as the slip length. It's proportional to the diffusivity. This is proportional to the inverse, the square root of the inverse to the diffusivity. And if delta goes to 0, you get plug flow. So we have all the ingredients already in the channel flow, and now we go back to our original model and do some. First of all, we know that alpha must be smaller than epsilon because we want to take this to 0. This is the situation we are in. And so we consider epsilon and delta be of order 1 quantities first and take the limit alpha to 0. This is what you get, plus more equations. I won't write them all down. The gist of it is that you get a singular limit as alpha goes to 0. Then you introduce a boundary layer coordinate and expand it. Write down the equations that solve the leading order problem. That is this one. So it's from then on, it's a very systematic calculation. And match it, and you get here now, and this is what we were after, this matched condition, which looks like that. So now, basically we have here a sharp interface model for the momentum and mass conservation, for the stress, and the boundary condition at the free interface, and the boundary condition, which is now the matched condition at z equal 0. And if you take this model and you can solve this, integrate this, you end up with this representation for the flow field. Now it goes very similar like the derivation of the lubrication equation. You see also that here you have, if you look at this ratio here, you get a Navier slip condition where 1 over delta H is your slip length, a singular slip in this case. And here's your lubrication model. So this is like a new lubrication model coming from the upper convected model when delta is of order 1. Are there other limits? Yes, indeed, at least one we found, and I think there are more. This is one when delta is of order epsilon. There's a distinguished limit when delta is, say, constant d times epsilon, and this is what it is when you do the calculation and the matching. So this is a coupled equation coupling the profile with the stress AZZ and the horizontal velocity. And in the limit, and that's what makes it interesting, when this goes to infinity, then you get AZZ being 1, and you recover our famous intermediate slip limit, even from the Maxwell limit. And so this is ongoing work. I think there are more limits. There are, of course, also more rheological models that could be analyzed in the same way as we did this year. This is the simplest case we could think of, and carries us a little bit further in explaining this complicated pattern you saw at the beginning by introducing some more microscopics into our continuum models. And by that, I thank also my many collaborators. I have, of course, not done this on my own, alone. So here, some of my collaborators, Andreas is sitting here, Tom Witelsky, John King, Markus Rauscher, Karin Jacobs, of course, Ralf Flosse, and so on, my former PhD student and another postdoc of mine. And as I mentioned before, this part of the work is collaborative work with Rich Brown and Pam Cook at the University of Delaware. And and I also thank various agencies for giving us the money to do this research. This is the Research Center in Berlin, Matheon, and the Priority Program of there's a DFG program in Germany on nano and microfluidics, and Occam in Oxford, I think, for giving me the chance for frequent visits and doing research. So, and you for your attention. Thank you.
Thank you, Barbara. Time for questions. When you go back to the last equation where you had this interesting mobility of h cubed and the linear term.
This one?
Before, the slide before.
This one?
This one, the final equation. So the delta was what? It was the inverse diffusion of the conformation?
Yeah, the inverse, the square root of it.
So if delta is larger, the conformation and diffusion is stronger or weaker?
It's the inverse of the diffusion, so if delta is larger, then the diffusion is smaller in the square. This is always the square root.
I mean, interesting is that if you imagine this equation to be a diffusion equation, with having the cubic term coming from them, having the proper energies for diffusion, also you would get exactly a linear term in H as a diffusion term. I mean, I'm not sure if this is a coincidence or whether this is some systematics behind.
Yeah, well, this model you actually do get. There's some very early literature on lubrication by Hu and Scriven, who introduced by having a thin film spreading on top of a porous medium. You get that equation actually, which is the singular slip. Which is interesting, but I haven't figured out why. Just coincidence.
I mean, if it has to be a polynomial, there are no dominant options.
Yes.
More questions?
This slippage, I'm just thinking about kind of the physics of slippage. As far as I know, I left this area some time ago, but people were looking at surface roughness as an important variable, like rubbing, scrubbing, or designing it at the nanoscale, etc. Is here it doesn't seem to.
It's a different thing. It's an apparent slip.
Yeah.
And it's so we don't take a simple liquid and make the substrate somehow complicated and rough or porous. But we're looking at a complex liquid and the response to a shearing force. The other one you're talking about, I don't want to get into. There are all kinds of theories with bubbles and what slip really is. But this one seems, even though the liquid is more complex, it's kind of easier to approach in a way. But well, easy is another thing. But it's a different thing.
I think the substrates, the experimental substrates, are really nanoscopically smooth.
Yeah.
In those experiments.
Yeah.
Actually, at some point we did a thin film model on a porous layer where we modeled the full Darcy Brinkman in the porous layer and the thin film on top, and you get actually up to the third power all terms. You can relate them to the porosity and the Darcy number.
Oh, that's nice.
questions? Remarks? Critique? Okay, so let's take a short break. Let's thank Barbara again and take a short break till Andreas starts at 3.